All right, so we are, just to scroll up here, we're in section 10.3, part 2. We're going to talk about arc length and surface area with parametric equations. Hypotrochoids, that's how you pronounce it. All right, so if we have everybody got all these or graphed all of these nice parametric equations. Okay. So yesterday we went through a process to come up with an expression for the arc length of a curve when we're using parametric equations. So just to back up a little bit, we said we have x equals f of t and y equals g of t, and we're on some interval a less than or equal to t less than or equal to b. And we said our curve didn't cross itself in the interval a to b, except maybe at the endpoint, so it might be a closed curve. So our arc length s was the integral from a to b of the square root of f prime squared plus g prime squared dt. So what I want to do an example of calculating arc length. As you can imagine, because of these, whoops, I forgot my squared here. Because of this radical and because of squaring all these things, you get interesting integrals that sometimes can be difficult to evaluate. And then we're going to take this arc length formula and talk about finding the area of a surface of revolution. So similar to what we did with functions where we had y equals f of x, following the same kind of progression, just and a similar development. So let's look at one of these. Let's look at one of these curves that we just wrote down, that a lot of us graphed. So we want to find the length of x equals cosine cubed t, y equals sine cubed t from 0 less than or equal to t less than or equal to 2 pi. So this is our asteroid. And if I sketch a quick graph, if you didn't graph these, asteroid looks something like this. And this is y equals 1, 1, negative 1, and negative 1. So what I want to do here, this is symmetrical. If you weren't sure what this looked like, you could graph it in your calculator and take a look at what it looks like. I'm going to find the length here in the first quadrant and multiply the result by 4, just to make work a little easier. So we need to find our derivatives first to plug into our arc length formula. So we're going to do, and I'm going to write dx dt squared. So let's write an expression for dx dt squared. So what is going to be the derivative of x with respect to t? I'll start us out. 3 cosine squared t times negative sine t, and we're going to square that. And when I square that all out, I get 9 cosine to the 4th t sine squared t. This is looking intimidating already. dy dt squared. So we're going to find dy dt. Dy, so we get a 3 sine squared t times cosine t. When I take that derivative, I'm going to square that, and I get 9 sine to the 4th t cosine squared t when I square it. And I'm going to look at this radical first before I start finding the integral. So the square root of dx dt squared plus dy dt squared equals the square root of these two quantities added, 9 plus sine to the 4t sine squared t plus 9 sine to the 4t plus sine squared t. All right. Hopefully this simplifies. What can we do with this? I don't want to integrate this. I want to simplify this a little bit. How can we simplify that? Take out the 9. Okay, there's a good start. Cosine squared and oops, I forgot my t sine squared t. And then what are we left with when we take those factors out? Cosine squared t plus sine squared t. Oh, thank goodness. That looks a little nicer, right? Cosine squared t plus sine squared t is 1. So then we just end up with the square root of this thing. So we end up with 3 cosine t sine t. Oh, we can integrate that, can't we? So we have the integral from 4 times the integral in the first quadrant. If I go from 0 to pi over 2, takes me up to this point. So I'm going to do my integral from 0 to pi over 2. And my integral is 3 cosine t sine t dt. And this is just a nice u substitution. I'm going to say u is sine t, du is cosine t dt. So this is 4 times sine squared t over 2. And we're evaluating that on 0 to pi over 2. So that turned out not too bad. What's that? 3, thank you. And we end up with 6 units. So this integral evaluates to 6 units. So the arc length of that asteroid is 6 units. So often with parametric equations, we end up having to do various algebraic manipulations in order to evaluate the arc length integral. And a lot of times the examples have to be some kind of set up kind of nicely so that we actually can evaluate that integral. Questions on that example? Isn't that a nice graph? Set of simple equations and you get this nice little thing. Okay. So let's talk about surface areas of revolution. Sounds like the way I wrote it sounds like the name of the title of a movie. Surface area revolution, or maybe a video game. Worst video game ever. For some reason, it made me think of the classic Tron video game where Tron's inside the little thing. That's what popped into my head. All right, so we have a smooth curve. So we're saying our curve is behaving nicely. We're starting with our parametric equations again: x equals f of t, y equals g of t. And it doesn't cross itself on AB. except maybe at the endpoints, so we could have a closed curve. And our surface area. And we're going to have two expressions depending on which axis we revolve about. So S equals 2 pi. We're making the same argument. We're looking at this little increment of arc length as, and I know it's our favorite word, our frustum of a cone.
Oh, yeah.
And we're revolving that about an axis. So we get the circumference of that revolution times the little area of that, or the length of that little piece of the cone, and we're summing that over the entire curve. So we get area equals 2 pi a to b, and I'm going to say g of t. G of t is going to be my radius when I revolve about the x-axis, and then the square root of f prime squared, our arc length increment, plus g prime squared dt, and this is revolution about the x-axis. And we want g of t greater than or equal to 0. So our radius is positive. And I think, so I'm going to say g of t equals the radius. So just like we did before, this is our radius of revolution, 2 pi. That gives us our circumference, and we're adding those little pieces of arc, rotating those around, adding them up along our curve. And then our second equation is just going to be the same expression, except for our radius changes when we revolve about the y-axis. 2 pi integral from a to b, and this would be f of t times our same arc length radical. And this is about our y-axis. And we want our radius to be positive. And here our radius is f of t. So exactly like we did before, we're just substituting our expressions for x and y and for our arc length that we came up with for parametric equations. And it's going to be convenient, as we'll use it more second semester, but this integral, this square root of f prime squared plus g prime squared dt, if we think of that as a little increment of arc length, and we call that ds, we can write that our surface area is, and I'll make my s big because I've been using a big S for surface area, integral from a to b of r of t ds, where ds is this square root of f prime squared plus g prime squared dt. So we're thinking of that as a little increment of arc length. And r of t is just our radius of revolution. And ds is this radical. So this arc length increment will be useful for lots of things when we start talking about surfaces, when we start talking about three-dimensional ideas, when we start talking about curvature. So using the arc length as a parameter, using the arc length for other things than just measuring the length, becomes very useful, and thinking of this in terms of ds, this arc length integral in terms of ds, is useful. All right. So questions on our formula. Not much different than what we've done several times in the past. All right. So what I want to do next is just one. I want to talk about a couple of standard parametric equations, and then we'll calculate an area, a surface area of revolution. All right. So as we go forward, as we work with these more, we'll be using these parametric equations, and you'll be given some shape, and being familiar with the parametric equation for that particular kind of shape is going to be useful. We've talked about an ellipse a little bit, so I want to talk about a circle. So let's see. If I have a circle x squared plus y squared equals 9. We want to write a set of parametric equations for that circle. So anybody have an idea what we might do? So use cosine t's and sine t's, right? Because we know that cosine squared theta plus sine squared theta equals 1. So it's going to involve cosines and sines. So I'm going to let x equal, my radius is 3. So I'm going to let x equal 3 cosine t, and y equals 3 sine t. And then when I square x squared plus y squared, I get 9. So our standard parameterization of a circle. So this was a good one to know. So our circle centered at the origin, radius r, is x equals r cosine t, y equals r sine t. So if your problem gives you a circle centered at the origin, you can immediately write a set of parametric equations for that circle. And the next problem will shift that circle a little bit and come up with a parameterization of that type of circle. So this one's a good one to know. Very similar to our ellipse, but circle problems come up frequently because circles are nice and they behave nicely when we solve problems. All right, so let's apply our surface area formula and then actually work on a problem. I just wanted you to see this because it comes up frequently. All right, so an example. We want to find the surface area of x equals cosine t and y equals 1 plus sine t for 0 less than or equal to t less than or equal to 2 pi. And we're going about the x-axis. So thinking about what we just talked about for a circle, what would you guess that the graph of this set of parametric equations would look like? Circle shifted up 1. So this is a circle. Center at 0, 1, and there's nothing in front of the sine and the cosine, so our radius equals 1. So when we revolve this about the x-axis, we'll get a torus. That's exactly right. So revolved about the x-axis, our radius is given by Which equation? It's given by y. So that's going to be our radius of revolution is the y coordinate of our little piece of arc length. So my arc length, the formula that I'm going to use, the integral, is going to be in general form a to b. I'm going to put the 2 pi out here, y, and then I'm going to just write ds for my arc length. My radius is y, and my arc length integral, or into little piece of arc length is ds. So let's write this out. So we get 2 pi, the integral from 0 to 2 pi. Y is 1 plus sine t, and I want to square the derivative of x prime minus sine t plus the square of the derivative of y prime, so I get cosine t, and this looking pretty nice, dt. So we get 2 pi, the integral from 0 to 2 pi of, what does this simplify to? 1. 1 plus sine t dt. Nice easy integral now. It looked intimidating at first, 1 plus sine t dt. And I evaluate that. I get 2 pi t minus cosine t evaluated on 0 to 2 pi. And when I evaluate that, I get 4 pi squared. So that would be my surface area. And this kind of, what my arc length here kind of reminds me of when we talked, what else did we talk about that was similar to this problem? Remember back when we were talking about centroids? Theorem of Pappus. Kind of reminds me, what we come up with kind of reminds me of the theorem of Pappus when we talked about finding the volume of a torus. Centroid, about the distance from the center of the centroid of the region, about the axis times the area of the region. Kind of reminds me of that. All right, questions on these two examples. Nothing that much different than what we've done in the past. We're just using our expressions for parametric equations rather than our standard explicit functions y in terms of x. All right. Homework. All right, there you go.